Dear students, today's lecture is about linear combination of vectors in the form of matrix. This lecture will tell us about vectors, that how could we write vectors in the form of a matrix. So let us start the lecture. Let us consider 3D vectors u, v and w. 3D vectors lie in space because there are three components of these kinds of vectors. This component is on the x-axis, and that is along y-axis. This component is along z-axis. So whenever you draw this vector, so this vector will lie in the space. Similarly, v and w. We have already studied that what is the linear combination of vectors. When we multiply these vectors by constant numbers a, b, c, we have multiplied this u by a, where a is a real number, and we have multiplied this v by b and this w by c, and then add these three vectors. So this is called the linear combination of u, v and w. So we have taken this linear combination of these three vectors. This can be written as a into u vector, that is u vector from here, plus b into v vector, this is v vector from there, plus cw, so plus c into w, that is w vector. Now simplifying this sum, multiplying this a inside will with all these three components, and multiply this b component with these components, and similarly this c with these components, and then adding all those au1 plus bv1 plus cv plus cw1, that is the first row element, au1 plus bv1 plus cv1. Similarly for second component, au2 plus bv2 plus cw2, that is the second row of this matrix. And the same thing will be followed for the third one, au3 plus bv3 plus cw3. So we have written this linear combination in the form of a matrix. We can write this sum in this form, just like if you have studied the matrix form of linear equations, that we will write x, y, z in the first row, then x2, y2, z2 in the second row, similarly x3, y3, z3 in the third row. So instead of x, y, z, there are u's and v's. So writing these u's, v's and w's in the first matrix, and a, b, c in a column matrix. So that is, if you look at this thing, if you multiply these matrices, so we will multiply this matrix with this matrix. How could we multiply this row with this column vector? So that will become au1 bv1 plus cw1, so that will be the first row. Similarly au2 plus bv2 plus cw2 is the second row, and similarly the third one. So let us denote this vector this vector is already denoted by u here. So this vector is, these components are actually the components of u. So this whole vector is u, and this whole is v, and these are the components of w vector. So that is a matrix containing vectors in the form of columns. That is the first vector u, whose components are in column form in this matrix, and that is the second matrix v, whose components lie in the second column of the matrix, and the third vector components lie in the third column of this matrix. So that is denoted by this matrix. This matrix, which is actually this matrix, is denoted by A, and this column vector is denoted by X. So you see that the linear combination of three vectors u, v, and w is written in the form of matrix times vector. This is a column vector. Linear combination of vectors is written in matrix times vector. So that is, this linear combination is equal to ax, and this a is actually in matrix. Times mean multiplication. A multiplied by x, so we say that a times x. So this is matrix times vector x. So the linear combination of vectors can be written in the form of matrix times vector. Remember that. So we say that in this case, we say that this A matrix acts on a vector x. This A matrix acts on a vector x. So whenever a matrix acts on a vector, so that will definitely the linear combination of those vectors. Now in this slide, there are some notes. The first one is we have just studied here that the linear combination of three vectors can be written in matrix times vector. We have just studied that. Now in this slide, we will be studying that the linear combination of three vectors is obtained by taking the dot product of rows of a vector, a matrix, with column vector x. From the previous example, ax, so that is a matrix. In the previous slide, that is a matrix, and times x, so this is x. Now whenever you multiply these two matrices, so that is row times this column vector, so that is just like that, au1 plus bv1 plus cw1. Similarly, au2 plus bv2 plus cw2, and thirdly au3 plus bv3 plus cw3. And this sum, this whole sum, is actually the dot product of u1 v1 w1 u1 v1 w1 dot abc, and this thing is the dot product of u2 v2 w2 and abc, and the third sum is actually the dot product of u3 v3 w3 dot abc. Whenever you taking the dot product of these two vectors, how could we take the dot product? The sum of the product of the corresponding entries AU1 plus BV1 plus CW1. That is the same thing. Similarly, the dot product of these two is AU2 plus BV2 plus CW2. And similarly here. So it means that if you multiply a square matrix or a matrix with a column vector, so that is actually row dot column. You see here, first row dot column. Similarly, second row dot column, third row dot column. So that is this statement means that is the dot product of rows of A. That is the first row of A. So rows of A, the first row, the second row, the third row, the dot product of rows of A with column vector ABC, with column vector ABC. So remember this statement, okay? Similarly, the linear combination of vectors u, v, w. What is the linear combination of three vectors? AU plus BV plus CW. That is the linear combination of these three vectors. This is obtained by sum of products of components of UVW with ABC. What does this statement mean? It means that is the linear combination. We have just studied that the linear combination of vectors can be written in the form of vectors time matrix times vector. So AX, and this AX can be written as A into U, the components of U, plus B components of V, plus C components of W. That is the meaning of this statement. Let's say let us take an example here. Instead of U1, U2, U3, we have taken a specific vector 1, -1, 0. Similarly, instead of V1, V2, V3, we have taken a specific vector 0, 1, -1. And instead of this W, we have taken this vector 0, 0, 1. And instead of A, B, C, we have taken X as x1, x2, x3. It is not necessary that you write here x1, x2, x3. You can write here A, B, C, but we have taken a vector B, a column vector B, whose components are B1, B2, B3. Then AX is equal to B. AX is equal to some B vector. So AX is equal to B. A is actually the matrix having columns U, V, and W, and X is this matrix column vector x1, x2, x3, and B is again a column vector B1, B2, B3. Now we need to calculate AX is equal to B. How could we calculate AX is equal to B? We have replaced U by its own components, V by its own components, and W by its own components, and that is vector X, that is vector B. Now the main thing here to understand is that how could we multiply these two? We can multiply these two by taking the dot product of rows with column vector. So the first one is the dot product of first row with this column vector 1, 0, 0 dot x1, x2, x3. Similarly, the second is, that is the second row. So second row, the dot product of this second row with x1, x2, x3. So that is the second row dot x1, x2, x3. And thirdly, third row, 0 minus 1 1, 0 minus 1 1 dot x1, x2, x3. that is from there, and is equal to b1, b2, b3. Now how could we take the dot product of these two vectors? 1 into x1 plus 0 into x2 plus 0 into x3. Similarly, that is minus 1 into x1 plus 1 into x2 plus 0 into x3. And here again 0 into x1 minus 1 into x2 plus 1 into x3. So I have written this dot product in some form is equal to b1, b2, b3. That will become 0. So 1 into x1 will be left here, and this will become 0. These two are left, and similarly these two are left here. So that is, this thing is equal to that thing. This vector is equal to this thing. In this slide we have written the same thing is equal to b1, b2, b3. Now again 1 into x1 is here, that will become 0. So that is x1, that is x2 is positive, so writing x2 first, and the coefficient of x1 is negative, so that's why I have written x1 here minus x1. Similarly, that is x3 minus x2 is equal to b1, b2, b3. Now these two vectors, column vectors, are equal to each other. So two vectors or two matrices will be equal if the corresponding components are equal. It means that x1 is equal to b1, or we may say that b1 is equal to x1. Similarly, b2 is equal to x2 minus x1, and b3 is equal to x3 minus x2 from there. Now if you want to find the solution of ax is equal to b, so that will mean that to find the values of x1, x2, x3. Now how could we find the value of x1, x2, x3 from these three equations? Obviously from the first equation we see that x1 is equal to b1. So using the forward substitution. What is forward substitution? It means that we will start from the first row and we'll go through the third row. So calculation which start from the first row and extend it towards the third row is forward substitution. And whenever the calculation starts from the third row, from the third equation up to the first equation, so that is called the back substitution. Now we see here, because we can find x1 from the first row, so that is forward substitution. From first row, row number first implies x1 is equal to b1, row number second implies x2 minus x1 is equal to b2. Now transferring this x1 towards that side implies that x2 is equal to x1 plus b1, but from the first row x1 is b1, so replacing x1 by b1, so that is the value of x2, b1 plus b2. Similarly, from the third row x3 minus x2 is b3. Now transferring this x2 towards right hand side, so that will become x3 is equal to x2 plus b3, but from the previous equation we see that x2 is b1 plus b2, so replacing this x2 by b1 plus b2 along with b3, so that is the value of x3. So the solution of ax is equal to b in this question is x1 is equal to b1, x2 is equal to b1 plus b2, and x3 is equal to b1 plus b2 plus b3. So the solution can be written in this form. x1 is b1. b1 can be written as the coefficient of b1 is 1 here, so 1 into b1 plus b2 is missing here, so we can write this as 0 into b2. Similarly, b3 is missing here, which can be written as 0 into b3. Similarly, this thing can be written as 1 into b1 plus 1 into b2. b3 is missing here, so that can be written as 0 into b3. And this equation obviously can be written as 1 into b1 plus 1 into b2 plus 1 into b3. So the solution in matrix form can be written as x1, x2, x3 is equal to matrix 1 0 0 1 1 0 1 1 1 times b1 b2 b3. Just look at this. Solution in matrix form x1, x2, x3 is equal to writing these numbers 1 0 0 1 1 0 1 1 1 in this matrix, and b1 b2 b3 in column form, so that is the solution of in matrix form. Now we see that if we denote this this matrix is obviously X matrix, and this matrix is obviously B matrix. Now this matrix is denoted by S here. This notation is used in your book. So we have denoted this matrix by capital S. From the previous equation, this is the solution of AX is equal to B. Now from here, A is removed from here, and that is transferred towards right side, which is this matrix, and this matrix is denoted by S. And we know that if there is a matrix, so when you transfer this matrix towards the right side, so that is actually the inverse of this A matrix. So in this case, that is for the system of AX is equal to B, the solution is X is equal to SB. X is equal to SB, and this S is actually what? The inverse of this A matrix. X is equal to A inverse B. So that is the solution of that system. So remember that whenever you find the solution of a system, it will mean that you need to find the values of x1, x2, x3, or in some sense you may find y1, y2, y3 if y's are given there, and the solution will be obtained by forward substitution. In that case, we see that in the coming slide we will study that what is upper triangular matrix and what is lower triangular matrix. So that matrix is actually, we see here that in the diagonal there are ones, whatever those elements, but non-zero. One of them must be non-zero, and above these ones there are zeros. Below these ones, all of them are not zero. So this kind of matrix is called lower triangular matrix. So that is lower triangular matrix. And if above, all of above are non-zero, and below these diagonals are zero, then we say that that is upper triangular matrix. Anyways, as a special case, that is the solution of this system. B1 is equal to x1, B2 is equal to this thing, B3 is equal to this thing. Those are equation 1, and these are equation 2. Now as a special case, if this solution x1, x2, x3, or x1 is say 1, x2 is say 4, x3 is say 9, we see that these numbers are the square of integers. What does it mean? This one is the square of 1. 1 square is 1. 4 is the square of 2. 2 square is 4. And 3 square is 9. So these are this vector is the square of integers. You can extend this vector up to x4, 16. You may write here 16, which is the square of 4. So 1 square, 2 square, 3 square, 4 square, 5 square, these components are the square of integers. So whenever the solution x1, x2, x3, the solution is the square of integers, then what will be the values of this column vector b1, b2, b3? So from equation 1, if you replace from this vector x1 is equal to 1, x2 is equal to 4, x3 is equal to 9. Now from equation 1, b1 is equal to x1. So b1 is equal to x1, but x1 is equal to 1. b2 is equal to x2 minus x1. So but x2 from this equation, x2 is 4 and x1 is 1. So 4 minus 1, that is 3. Similarly, b3 is x3 minus x2. Now x3 from this equation is 9 and x2 is 4. 9 minus 4 is 5. And we see that these numbers are 1, 3, 5. These numbers are odd numbers. So it means that the sum of first 3 odd numbers, the sum of odd numbers is the square of integers. 3 integers. The square of 1, the square of 2, the square of 3. Anyways, for example, if say let b is those odd integers 1, 3, 5, then we if you want to check that if this vector is 1, 3, 5, then what will be the solution x1, x2, x3? So putting these b's, b1 is equal to 1, b2 is equal to 3, b3 is equal to 5, put these b's in equation 2 here. x1 is equal to b1, x1 is equal to b1, and b1 is 1. This one can be written as 1 square. Similarly, x2 is b1 plus b2. So b1 plus b2. b1 is 1, b2 is 3, so 1 plus 3 is 4. 4 is actually 2 square. Similarly, from the last equation, x3 is b1 plus b2 plus b3. So b1 plus b2 plus b3 is 9, and 9 is 3 square. So whenever we replace this vector and the components of this vector are odd numbers, so the solution is the square of integers, positive integers. In this slide, we will study that what does main diagonal mean. Main diagonal, the second name of main is principal diagonal or leading diagonal of a square matrix. A square matrix is that matrix in which number of rows and number of columns are equal. In this matrix we see that number of rows, first row, second row, third row, fourth row, there are 4 rows and there are 4 columns. So this is a square matrix. The main diagonal of a square matrix or the leading diagonal of square matrix is from left to right. When you are coming from upstairs to downstairs, so that is from left to right. This is the main diagonal of a square matrix. Now we are in position to define lower and upper triangular matrices. What is a lower triangular matrix and what is an upper triangular matrix? We see here lower triangular matrix is noted by L because of this L, and upper triangular matrix is denoted by U because of this U. Lower triangular matrix, a square matrix in which above this main diagonal all entries are 0. and below this main diagonal, not all of these entries are 0. There may be some zeros, but not all zeros. If above this main diagonal all entries are 0, that is called lower triangular matrix. And if below this main diagonal all elements are 0, then we say that that is upper triangular matrix. So we are in position to solve problem set 1.3. Question number 1 is an easy question. Question number 1 says that find the linear combination 2s1 plus 3s2 plus 4s3 is equal to b. So what is the linear combination 2 into this s1 plus 3 into this is 2 plus 4 into this is 3 is equal to b? You may write this b as b1 b2 b3. The components of b are b1 b2 b3. Second is, then write b as a matrix vector multiplication sx. What does it mean? Find s, where s contains all those columns, this column, this column, then this column, multiplied by x. X is actually 2, 3, 4, a column vector, is equal to b. B can be written as b1 b2 b3. Question number 2, solve the system this with s1 s2 s3 in the columns of s. This is s1, this is s2, this is s3, and y is this thing. So instead of x's there are y's, y1 y2 y3, and this is vector b. We need to solve this equation. So how could we solve this equation? Multiplying these two matrices by that definition that this is the dot product of rows into columns, and then comparing by comparison, find y1, then find y2, then find y3. That is the solution of this system. Similarly, follow the same criteria for this system. So these are actually two equations, and from that thing the sum of the first n odd numbers is n square in the previous example. Solve the system of equation for y1 y2 y3 in terms of b1 b2 b3. You need to solve this system. What is the solution? Solution is actually y1 y2 y3. You need to find the values of y1 y2 y3, multiplying these two matrices by the dot product of rows into this column, and then find y1 y2 y3 in terms of b1 b2 b3. Write the solution y as a matrix A is equal to S inverse. So how could whenever you find the solution, whenever you find the values of y1 y2 y3, then write that solution, write those values of y in the form of a matrix which will be on that side, which is actually S inverse. Are the columns of S independent or dependent? Leave this topic because it have no concern with our topic. So solve it up to here, and the same criteria is extended to 4 by 4 matrix. You need to, moving 4 by 4 difference equation Ax is equal to b, find the 4 components x1 x2 x3 x4. You need to find x1 x2 x3 x4 in the form of b's. Then write this solution x is equal to sb, converting when you multiply this thing, find x1 x2 x3 x4, and then write x1 x2 x3 x4 in the product of this matrix into S matrix, and find the inverse. So that matrix S will be actually the inverse of this matrix, and this question is the same as these questions. So try to solve these questions, and if there is any difficulty, any problem, then we'll discuss this afterward.